All right, let's go ahead and get started. All right, so hello everyone and welcome to the very first Scilab security seminar of the semester. So today we're excited to have our very own graduate student, Xiqing Ma, present to us about his work with his advisors, Dongyan and Zhang Yu. So I was just at Usenix Security last week, so the title slide doesn't say it, but this paper actually was the recipient of one of the Distinguished Papers Awards at Usenix Security. So I'm excited to have hear some of the very best work from Usenix Security. So thank you, and I'll let Xiqing tell us all about it. Thanks.
Okay, thank you. Thank you, Professor Blocky, for the introduction. So, hello everyone. I'm Shiqing Ma. I'm here studying in the computer science department. This work is called MPI, Multiple Perspective Attack Investigation with Semantic Aware Execution Partitioning. This work is a joint work with Professor Juan Zhai from Nanjing University, my colleague Fei Wang, and Professor Q Han Li from University of Georgia, and my advisors Xiangyu Zhang and Dongyan Zhu. So before we start, I would like to first go through some backgrounds. First, the work is in the context of attack investigation. So traditionally, attack investigation has two components. The first one is a provenance system. So what is provenance? Basically, it's a history. So provenance tracking system basically will log all the activities on your system for like Windows or Linux or even Android platform. They all have provenance systems logging the processes and objects like files and sockets activities. And there are many ways there are many existing provenance systems. For us, we use a Linux audit system. It's actually built in the Linux mainstream kernel. And some other researchers actually use others like Linux security module to monitor all the inodes and log all the activities. A very typical log will look like this. For each event, it will have a process and operations on some system objects or subjects, like a PID represents one process. The process is receiving packets from some sockets, and the process can write or read to files. We do this by monitoring all the system calls, the Linux audit framework, and we can log all the important activities for individual system objects like file sockets and processes. The second component is called the dependence analysis. So basically, it will analyze all the events happen in your system and try to build a causal graph. A causal graph basically represents all the dependence in the system, and it will represent everything that happened in the system. For dependencies, there are many types. For example, process to process. Basically, process creates another process or terminates, send a queue to another process, or process to sockets or files, create, bind, open, or close, delete. And a causal graph will look like this. So basically, the edges represent the causal relationships, and the nodes here will represent the system objects or subjects. Like we use different shapes to represent different types. Sockets is a diamond, and a process like a triangle. And here is an overview. So the left-hand side shows two log entries, and the right-hand side will be the graph generated from the two log entries. So as we can see, process 24 actually reads some information from socket and write to a local file task man. There is an information flow from the socket to the process and then write to the socket. It's pretty clear After these two steps, when you get the causal graph, it's pretty clear what has happened in the system. And this will help the investigators to understand the system activities. And this is a traditional way of doing this. This one actually shows a real-world example. It's I think it's just 5 minutes using a few programs. As you can see, the graph is pretty big. It contains hundreds of nodes and thousands of edges. This is because this is real life, because there are many programs running on your system at the same time, and they all have interactions with each other. The causal graph actually is good. You can easily understand it, but the size is too large. The complexity makes the investigation pretty hard. And the fundamental problem here is called the dependency explosion problem. And I'm going to introduce the problem and some related works. So here I will show a very simple example. It's a phishing attack by email. So this is one email. It's a typical spam email, but they usually have titles like urgent or important, and they fake the senders. Like this one is from Chase Online. Everything looks good, and actually when you click the link here, it will redirect you to a web page. The URL and the page looks benign. It's so malicious. But if you click the download activity, it actually will download you a malware. So this is a traditional attack, traditional phishing attack. And whenever I think most of us will have the antivirus program running on your system. If you don't, please install one. So whenever this alert happens, this is how the investigation happens. So the investigation actually happens after you actually know the attack already happens, because eventually malware will expose itself. And this is a simplified graph generated from the previous example using the traditional approach I just introduced before. As you can see, there are many nodes here. Some of the nodes are pretty important. For example, send mail process, and the email client process, and the Firefox process. As you can see, those are the hot nodes. They connect to other many thousands or hundreds or thousands sockets and other processes, which makes the graph very complex and hard to understand. The dependencies, here are some simple numbers. The previous graph has 51 processes, 15 files, more than 250 network addresses, more than 350 edges. But the attack is pretty simple. Typical, it's a very simple attack, but the graph looks very complex. That's because of the dependency explosion problem. Because the graph actually have many bogus dependencies. Here are the red nodes in this graph actually shows the attack path. So one email basically is just from one sender, and the email or the download events, the click events from the email client, and the download events from the Firefox, they are pretty simple activities. The source of the downloaded malware, it has only one source, right? It's just from one socket. In normal cases, you don't really download one file from like thousands of sockets. But the graph shows many nodes. Why? This is a dependency explosion problem. It's because the traditional approach actually have one assumption. Every write depends on all the read events that happen before it. So, for example, you are using Vim to edit one file. You probably will open many files at the same time. You will have many read events, but one write events. Actually, you are editing different files, but from the provenance perspective, you don't really know, because you already lost the context. You don't know the context of the application. You just know the context of the system. So the system tells you, okay, you read many files and you write to another file. The dependency analysis will have to assume all the read are the sources, and the one write event is writing to the destination. This assumption is clearly wrong, but we can't really do anything if we use existing systems. Researchers actually have noticed this problem and proposed the solutions. It's called execution partitioning. You may still recall my title. I have the execution partitioning keyword here. The basic idea is actually those processes, those actually the hot nodes in the graph, they are actually the nodes that cause the problems. Because those programs actually run a long time, and many read events and write events happen, and because of the assumption, actually it will introduce many bogus dependencies. The basic idea of execution partitioning is to partition the process into multiple processes, as you can imagine. So here is an example of the Firefox. Firefox, if you visit many sockets, visit many websites, it will have many socket reads, and it writes to one file that has only one file write. But if you use a traditional approach, the write events will depend on all the previous socket reads, and the graph looks like this. Only one socket is a true source, and all the others will be bogus. The idea of execution partitioning will just partition Firefox to individual execution units. So each unit will just handle one socket. So when you do the backward analysis from the file, you only trace to one socket, and the dependency won't propagate to previous sockets. That's the basic idea. But obviously, individual units can depend on each other. So it's called inter-unit dependence. The assumption in this model will be different. So in this model, all the events happen within one unit will have the causal dependence. We will analyze the causal dependence. And all the events that happen in different units, by default, we assume they don't have a dependence. So that's how we stop the propagation of the dependence. And by leveraging the inter-unit dependence, actually this will complete the graph. We actually won't lose any necessary dependence here. So existing execution partitioning technique, the state of art is called BIP. It's based on the event handling loop. So as we all know, the current operating systems, most of the programs are actually event-driven programs. When external event happen, the program receives this event and calls the corresponding event handler to process this event. This is why they actually run for a long time, because there are a very large number of external events. So the idea of BIP is actually instrument one event at the entry of the event handling loop, and one unit exit event at the end of the execution unit. And everything in between, all the events happen after the unit enter and before the unit exit will be considered as one unit. So all the events here will belong to one execution unit. And when we analyze the causal dependencies, we actually will just consider the events happen within this unit if there are no inter-unit dependencies. So basically, no, the name BIP is for binary-based execution unit. It's actually published in NDSS 2013. It proposes a fine-grained subject. Basically, the processes will be individual units, and they can be connected by inter-unit dependencies. This is a BIP generated graph by applying on the previous example, all the red nodes here are still the attack path. So all the blue nodes actually can be removed from this graph. And this is the final result. As you can see, it's pretty clear. It's just one line. And the attack path and all the sources, what happened in the system is now very clear. This is a comparison. So BIP actually can reduce a lot of bogus dependency in the graph. But this is not our, this is not MPI. We like that. Yes.
So my question is, do you get to this point because you're referencing some place that has noted this malware, and therefore you kind of reduce these different indicators in processes and files and network addresses, and you can stop it before it happens? How do you collect this information to kind of neck it down as you have?
You mean, I don't fully understand your question.
So your process allows you to reduce what you have to watch, correct? And respond to.
Yes.
How do you figure out, do you have to actually get attacked by the malware to create this isolation? Or are you reaching out to someplace in the cloud and getting these indicators?
The indicators you mean, because the event handling loop is in the program, right?
Okay.
You actually can analyze. We use pin tool to analyze the binary and perform the instrumentation. Basically, the BIP will need the binary rewriting to instrument the special system calls at the enter and at the exit point of the event handling loop. Event handling loop is not very hard to identify because it's more than 90 of the execution will be the event handling loop. So you just need to monitor the hot paths during runtime, use the pin tool, and you can easily identify the execution.
May I rephrase what I think you told me to make sure I have it correctly? So what you're saying is this loop that you've identified as an event is identifiable so
Yes.
that you can see it coming potentially before it happens.
Yes.
Thank you.
And well, actually, we have been using BIP for a long time. It works pretty well to solve the dependency explosion problem, but it has many limitations. First of all, it has many low-level events, like the GUI programs or the mouse click, keyboard strokes, are actually external events. The event handling loop will actually have one event handler to process this event. It will generate many low-level events. Those events cannot directly be mapped to the high-level events. We generate a graph actually to understand user intentions. But those low-level events actually makes the graph even harder actually. For example, you are typing a URL in Firefox. Every keystroke will be one execution unit. You have to change them to actually get to know you're actually typing here. The second one is for the inter-unit dependencies. Inter-unit dependency is very hard. It's because the inter-unit dependency has to be a memory location. Inter-unit, you have to monitor all the memory accesses to actually identify all the read and write events and constantly find the constant relationship between two different units and identify such inter-unit dependence. So for us, we have to actually have hundreds to thousands test cases and use the pin tool to monitor all the memory accesses. The pin tool is pretty slow. For people who haven't used the pin tool, I can say it's about 10 times slower. So imagine you are using Firefox like 10 times slower. It's horrible. It's not a very good experience. So the process to identify the inter-unit dependence is actually very heavy. And the BIP actually also generates many useless units, like the mouse movements. Those signals from the hardware are also external inputs. This will make a lot of unnecessary units. So what is really desired from the investigator's point of view? So first of all, we want to have a meaningful graph. Basically, when you see the graph, you know what happens. That will be the best goal. Like for Firefox, if you see one node in the graph, okay, we know it's one tab, or we know it's one page. It will be better. People will just directly understand, okay, this socket is representing one page, or it's one tab. And the second is investigating actually requires many different perspectives. Sometimes fine grained will be good. Sometimes tab grained the coarse grained will be better. It totally depends on the different types of attacks. And also actually, this is related with causality model, where you want to track the causality or not. Also for the causality, we also want to remove the training process for inter-unit dependence. And then we want to make the log smaller. This note removes all the unnecessary units. This will not only remove the entries from the log to reduce the space overhead, but also remove the unnecessary instrumentations. This will save some of the runtime overhead. MPI is proposed based on the desired goals we want. It's actually inspired by process isolation mechanism in current operating systems. The basic idea is to let the investigator to define what you want to trace. What is the execution unit you want in this program? So we call this a user-defined task. So we will partition the program based on the definition. If you define different tasks, actually we can partition the program in different ways. Those will provide the investigators different perspectives to look at the attack. And the task is usually represented by different types of data structures, like Firefox one-page tab window or individual DOM elements. The basic workflow is programmers or the investigators first will have to annotate the program to tell us, okay, this is the perspective of the task I want. And then we will use our LLVM chain with some customized passes to actually compile the program, perform the analysis and the instrumentation, and then generate the executables. The executable will actively exposes the unit information to the provenance system. So the provenance system will collect those information, and when you perform the analysis, you know the events within individual units. We also provide another miner. It's called the Annotation Miner to help the programmers annotate the program, because I think it's not very easy to understand like the source code of Firefox or Vim. So the first of all, our technique, annotation. Annotation is actually very popular. I think including Linux, Firefox, Vim, basically all the softwares currently are using the language extension. It's supported by GCC and clone, basically by the most of the compilers. It's widely used. For Firefox, we have observed more than 900 different types of annotations. And for just the NS stack class, this annotation is to make sure the class is in the stack, not in the heap. It has more than 400 annotated classes. And the last bullet actually shows the format of the annotation. You can define your own annotation string and perform analysis in the IR level. will add metadata in the IR. So first, let's talk about the annotations we need for this task. As we said before, our MPI is inspired by the operating system isolation mechanism. So first, review the OS process model. One process has its own ID to identify the process. And whenever the scheduler picks up another process to run, it will update the current value in Linux kernel. And this current represents a current running process. Also, processes can have a data exchange by using IPCs. For example, like pipes. And the apps, it has a very similar model. The application programs, basically it deals with individual tasks. Those tasks are annotated. And to identify individual tasks, we define one annotation. It's called identifier. It's just like the PID in the process model to identify the individual tasks, and one indicator to indicate the switch between tasks. And similarly, we have IPCs, and we have the channel annotation representing the data exchange channel. Indicator is just like the current variable in OS. It basically tells us, okay, we are switching the context in the application. So this is the place we actually perform our instrumentation. When you tell the provenance system, oh, hey, the context is changing. And the identifier basically tells which task it belongs to. So this is also some of the information when you tell the provenance system. When you tell, hey, I'm currently working on this task A or task B or task C. And the third one is a channel. It's just like IPCs. I think we are good here, right? It's very easy to understand the annotations. The example is Vim. So in Vim, you can have one window, but opening different buffers. And the different buffer you can edit in different files. So if we perform, each buffer is represented by the buff_t data structure. And in the buff_t, it has its own ID. Basically, you need something to identify the data structure instances. So the buff ID will be annotated as the identifier. And there is one global variable in Vim called curbuff. It's of the type buff_t. It's a pointer. It's actually pointing to the current buffer the user is editing. Basically, it tells which buffer the user is working on. And in Vim, we have a channel annotation. It's because of Vim's built-in clipboard. So in Vim, if you use copy and paste, you can actually use the clipboard built-in Vim to copy and paste contents to exchange data between different buffers. The buffer is in Vim is known as a register, YANK register. We annotate the current YANK register as a channel variable. So this is an example of the context switch. So do E command, E means edit. When you type this command, you will switch a buffer. So the curbuff will be assigned a new value. We will instrument some code after this statement. So basically, it will first check if the buffer is really changing or not. If it changes, we actually expose the current buffer ID, basically the new buffer ID, to the provenance system. For different provenance system, we actually use different functions. The function is different. For Linux audit, we use the Q system call with illegal parameters. -100 is all the PIDs will be larger than 100, will be larger than 0, so this value is illegal. So whenever it calls to the kernel, it will directly actually returns, so to save some time. To help the annotation, we developed the Annotation Miner. As we said before, those tasks are usually represented by some application data structures, like the buff-t we shown before in Vim. Our Annotation Miner is used to help the developers find such data structures. So we also use Vim as an example here. We are using the differential analysis. First of all, we generate one test case A. We perform very traditional, very normal operations, open, edit, and save the file. And in the runtime, we will monitor all the different types of data structures. We will log the number of instances for this type. And for type test B, we actually basically duplicate the task twice. We do the task in A twice, but in two different buffers. So the only variable here will be just the number of buffers. And at runtime, we also collect the number of instances for individual data structures. And then we compare the two results and merge them into one. As you can see, the only difference here is the number of buffers. We basically double the number. And many data structures will only have one instance. It's not related with the task. If the data structure is related to the task, the perspective you are using, it actually the number in test case B will be the double of the number in test case A. So like you're editing two files, obviously you will have two opens, right? So this is intuition. For like example like logging, you only have one log buffer in your application. Obviously, no matter how many files you are editing, it's gonna be only one. And we remove some of them and choose some candidates. In practice, we found that even though we remove some of them, we still have many. This is actually because like the buff-t case, it has many fields. Like post-t is representing the current editing place. Like line, it has two fields, the line and the column number. I mean, if you have two buff-t, you're definitely gonna have two post-t's because it's one field. So we perform another analysis. Basically, we just try to identify the top level data structure and report it to the user. By doing this, the post-t, those will be removed. Only the buff-t will be reported. And now I'm gonna talk about the thread model in applications. This is I'm using Firefox here because the Vim is just a single process. It's too easy. Firefox, first let's review the page loading process. First, DNS, right? When you type the URL, it will first query the DNS. It will actually send one query to the DNS thread. The DNS thread will perform the querying and return the results. If you are using different tabs, the different tabs will all post events to the DNS thread. And when they return, it will start to load. At first, it will create sockets and for the communication, and then send the HTTP requests to the servers. The socket thread here is actually for creating and communicate with the remote servers. The main thread is usually just for rendering. This is for performance. I mean, we all use Firefox. Basically, we open like 10 tabs at the same time. I mean, many tabs are active. You can't just depends on only one thread to do this. The response time will be too long. It's basically unusable. So, but if you review the DNS thread and the socket thread here, we will find some problem. It just receives events and then processes the events and then return. It actually doesn't know the global context. Like in the DNS thread, it receives the individual events, but frankly speaking, it doesn't really know which tab is requesting this DNS. And we call those threads worker threads. Those worker threads, they only work on one type or actually a very limited number of types, and those types usually are very similar. And those tasks are, we call them subtasks. They are not like top level tasks. Top level tasks will be like tabs or pages, but those top level tasks will be divided into individual subtasks and dispatched to individual threads, and the main thread will gather the information and then render the page. They don't really know the global context, so when we attribute the events happen in the worker thread, we actually don't know how to attribute them to the global task. We actually don't know the global context. To solve this problem, we introduce the delegator annotation. Delegator annotation, basically we need to instrument the data structure for the subtasks to actually inherit the task identifier from the top level data structure. So this is an example. The left-hand side actually shows the NS connect events. In Firefox, it's a connection event. So HTTP, FTP, and whenever the main thread wants to connect to something, it will post the NS connect event to the socket thread. Previously, we know the socket thread doesn't know the global context, but when the NS connect event is, whenever we have a new instance of the delegator class, we instrument another line to inherit the current ID, inherit the current global context. And when this event is eventually dispatched to the worker thread, the worker thread actually, by nature, it will know the global context. And all the events happening in the worker thread can be correctly attributed to the global identifier. By doing so, all the events, even for multi-threaded programs, all the events can be correctly attributed to the global context, and those will form one unit. And in the rest, I will show some evaluations. First is annotation efforts. Surprisingly, the annotation efforts is kind of pretty small. The first column is application. The second column is the program size measured by line of code. And those four columns show the annotations for different types. ID is the identifier, IND is the indicator, channel variable, and delegators. The last one shows the instrumented code, instrumented places. So our LLVM path will automatically perform the analysis and perform the instrumentation. This table is just to show the annotation efforts is pretty small. But the instrumentation, as you can see, is usually a few hundred to a few thousand. So basically, you cannot really do it manually. And Firefox has a maximum number of annotation and also the instrumentation. This is because of complexity. As you can see, the line of code of Firefox is it's very large. It's a very big and complex program. So this table shows space overhead. By space overhead, I should recall some. So we perform the instrumentation to tell the identifier to the provenance system. Like Linux audit system, we actually use the queue system call. Those are actually additional system events. Those will help the analysis, but it will also consume some space because it generates additional system events. And we don't really want too many additional system events. This evaluation is used just to show the number of additional system events caused by the instrumentation. The first column is the number of the application. The second one is the perspective we use for MPI. And the next two columns show the comparison with BIP. We use two different provenance systems. One is a links audit system. The other one is Hi-Fi. It's another very popular provenance system just published in exec 2013. And the last two columns shows the numbers for MPI on two different provenance systems. As you can see, for Firefox, the space overhead caused by BIP is very high, and comparing with BIP, MPI performance is better. This is because the low-level events in Firefox, many of them can be actually removed. So we actually can remove those unnecessary instrumentations and make the instrumentation lightweight. But for other programs like Bash, in Bash, basically one event handling loop will just be one user command. I mean, it's already very high level. So the MPI partition and the BIP partition will be very similar, because BIP doesn't really generate many redundant events. This is the evaluation for the space overhead by using different perspectives, basically annotating different data structures. For Firefox, we have a window and a tab and element. Window basically means the top level big window using the system headers and stuff. And the elements actually individual DOM elements, including iframes, all the placeholders, and also the DIVs and the images, the links, everything. It's very heavy. And for Apache, we use the connection and the request. For since HTTP 1.1, a connection can be long-living and have many requests. So those are the two perspectives used in Apache. As you can see, the more fine-grained, basically, the overhead will be very high. Like the DOM is basically is more than 40%. And this is the evaluation for the runtime caused by instrumentation. In general, it's small, less than 1%, which means it's good. And the last one will be just showing a case study. Just a very simplified example. As before, we use Firefox to download a few files and download some torrents, use the transmission program. This is a traditional program. This is a traditional solution. The two processes causes a lot of bogus dependencies. This is a BIP. It's actually pretty. It's correct. All the dependencies are correct. It's just the number of internal events in Firefox causes this problem, makes it looks even worse than traditional. This is MPI. MPI using tab perspective. So we first use Bing to search and open a few tabs and download the files, and use a transparent program. It's much more clear because we removed all the redundant events in BIP. And this one is another perspective, using basically the websites you visit. Actually, we can merge all the tabs visiting the same websites into one node, makes the source of the downloaded files even clearer. So this is just to show the power of using different perspectives. There are many related works. If you are interested, you can read some of them. And of course, we have limitations. First of all, we need the source code. It's based on LLVM. We have to. And I think it's necessary because the user have to provide the perspective to us. The second one is annotation. It's not fully automated. We have the miner, but we just identify the data structure. Actually, we need to identify the indicator and identify our variables. Still one more step to go. And as a conclusion, we proposed the MPI, an execution partitioning technique based on high-level data structures. It allows the user to actually annotate the high-level data structures and we will perform the instrumentation to capture the events, including unit context switch and its delegation. We implemented the prototype, and the evaluation shows we actually support we actually have better investigation support by providing different perspectives, and the overhead is pretty low, especially comparing with state-of-the-art BIP. And thank you. I'm gonna take questions if you have.
Thanks. All right. Are there any questions for Xiqing?
Yes.
So, are you looking at other browsers?
Are you looking at other browsers besides Firefox?
Yes, we actually in the paper we have many more evaluation results. The slides only show only a small portion of it. We have other browsers like W3M. We didn't really look into Chrome. It's because the execution model of Chrome is well partitioned already. So Chrome actually you can compile the open source version by actually have different compile flags. You can actually have one process just for one tab. So it's well partitioned already. Also, it's in a sandbox. I mean, I like the design, but it makes the life easier. But yeah, doesn't apply here. Thank you.
All right, so I'll ask a few questions. You mentioned that you need the source code and you rely on programmers to kind of annotate the source code.
Yes.
I was curious if you've done any investigation into how accurate programmer investigations or programmer annotations are. You know, what happens when the programmer makes a mistake? Do you start to miss critical events in the log?
Okay, thank you for the question. So the MPI is heavily depends on the annotations. We develop the Annotation Miner, try to make the errors as less as possible, but it still is unavoidable. I have to say this, but what I want to point out is actually the log is still complete, but it will only affect the analysis. So maybe one event is attributed to another different unit. Still, the event is in the log. If you want, you can still generate the choreograph using the traditional approach, and the graph will be still complete. So we don't really lose anything. It's just the accuracy of the analyzed results. Thank you.
All right. Any other questions? All right, let's thank Xiqing again.
Okay, thank you.